Hello everyone, in today's class we're going to look at heat transfer in a cylindrical tube or pipe. So to start off, let's draw a diagram of a cylinder. That's the first diameter and that's the second diameter. Okay, and that is our pipe right here. Okay, so this here is our first radius R1. This is our second radius R2. This is temperature 1 and that is our temperature 2. So the heat diffusion equation for a cylinder is, I'm just going to copy it from the book. For the plain wall we drove the equation, but for the cylindrical heat diffusion equation I'll just write it out from the book and you can see the derivation there. So in the textbook it's equation 2.26. Okay, heat diffusion for a cylinder. Okay, so the equation is 1 over R times d over dr times kr differential T over differential R. Okay, that represents the heat flow in the R direction. Okay, plus 1 over R squared d over d theta times K times differential T differential theta. Okay, this is the heat flow in the theta direction, meaning the in an angle, the heat diffusion in an angle. So for example, if we're looking at this tube here, this tube has 3 dimensions. One is the radius axis, where heat flows in the radial direction, and in an angle direction, which is like this. That here is theta, an angular direction, which this term represents. This represents the heat flow in an angular axis or an angular direction, and the third direction is the z direction, which is in axial direction of the cylinder, which is the third term. Plus, let me write it down here, plus d over dz times k dt over dz, and that represents the heat flow in the z direction, plus q dot, which represents the energy being generated inside the system, equals energy being stored, which is density times Cp dt over d time. Okay, now just like the plane wall, we're gonna have the same assumptions that we're working with a one-dimensional, and the dimension we're working with here is the R axis, the radial axis, meaning that heat will only be flowing in the radial direction. It's not going to be flowing in the axial direction or in an angle. It'll be in the radial direction. Okay, so that being said, one dimension, we can go ahead and eliminate the other dimensions. Theta is 0 and the z direction is also 0. So that's the first assumption. The second assumption is we're assuming that it's taking place in steady state, meaning that the energy stored equals 0. Therefore, this term here is 0. The third assumption we're assuming is that there's no energy being generated. Okay, therefore Q dot is 0, and the last and not least, constant K value, meaning that K is not a function of temperature. Therefore, this K we have here can leave the differential and can come outside the differential. Therefore, after canceling all these terms, we'll be left with K over R d over dr times R dt over dr equals 0. Okay? We can take this term to the other side, times it by 0, and we'll be left with d over dr bracket times R dt over dr equals 0. Now, a derivative of something that gives me 0, that means that whatever is inside this bracket has to be a constant, because a derivative of a constant will give me a 0. Therefore, R dt over dr equals a constant, equals a constant. If we simplify this more, we'll get dt over dr equals C1. Therefore, if we take this dr to the other side, I think I'm missing something. Yeah. Sorry about that. Let me erase this. So we'll take the R went, this R here, it went to this side, was divided by this side, so divided by R. Now, I'll take this dr to the other side here, which will look like dt equals C1 over R dr. If we integrate both sides, 0 to R, or it could be from R1 to R2, okay? But I'll just leave it from 0 to R. Therefore, we'll get temperature as a function of radius will equal to C1 ln R plus C2, which will give us a logarithmic function. Long function. Okay? Meaning that if we look at the temperature distribution in the cylinder throughout this, or in the cylinder, it'll be, so if we assume this is the R1, R2, T1, T2, we'll get R1 and T1, R2 and T2. I think I mixed it up. Yes, I did. T1 is up here because T1 is higher than T2. T1 is higher than T2. And as you can see here, we're assuming that the fluid going into the pipe is what's causing the heat transfer. Therefore, T1 here, this point, since it's closer to the fluid, will be hotter than this point there. So T1 will be higher than T2. Okay, so let me correct this. So R1 will have a higher temperature than R2. Okay. The temperature distribution is logarithmic, like that. That is for the cylinder pipe. Whereas the plain wall was linear, if you remember from chapter 1 and also the beginning of chapter 2. So that is your T1, T2, 0 to L. That's 0, and that's L. And the temperature distribution in the plane wall was linear. Linear, logarithmic. Okay? Logarithmic. Okay. So let's write down the function we found, which is a logarithmic variation of the temperature in a cylinder. We found that to be TR equals C1 ln R plus C2. Now the next step we need to do is find C1, C2. To find C1 and C2, we need to use the boundary conditions. One, that the temperature at R equals R1, that will give us T1, and at the temperature where R equals R2, that will give us T2. Now you can apply these two boundary conditions to find C1 and C2. I won't be doing that in this class. You can go back to the textbook to see step by step how it was done. But the temperature distribution that you'll get will be TR equals T1 minus T2 divided by ln R2 over R1 times ln R over R2 plus T2. That's after inputting the values of C1, after finding the values of C1 and C2 and entering them into the equation. Okay, so that is the temperature distribution or variation in a cylindrical pipe or tube. Okay, now in order to find the heat transfer, which heat is being transferred by conduction, and as we reviewed in chapter 1, conduction is negative K A dt over, in this case it's dr, it used to be dx, but because the dimension that the heat is flowing in this example, or in this situation, is the radial direction, so we'll be working with dr. Okay, so the next step is to find the derivative of this equation here in terms of dr. Okay, and that will be dt dr. Let's write that down here. dt dr will equal to you know what? Let me just write the whole equation. Q equals 2 pi KL over ln R2 over R times T1 minus T2. Okay? We can rearrange this equation to make it similar to Ohm's law. If you remember, in the previous two classes we covered on that. So Ohm's law is current equals change in voltage divided by resistance. So we can rearrange the heat transfer to look something similar. Therefore, it will be T1 minus T2 divided by ln R2 divided by R1 over 2 pi KL. Okay? Which can be also written as dt divided by resistance of a conduction pipe. Okay? Our conduction pipe will equal to ln R2 divided by R1 2 pi KL. That's the resistance for a conduction in a cylindrical pipe. It will also, if we want to draw the thermal circuit for that, it will look something like this. So heat transfers from the higher temperature to the lower temperature, and the resistance, some heat is lost to the resistance, which is a conduction of a cylindrical pipe that we found over here. And that's pretty much for this video. So far we covered sorry, we covered a convection resistance, which is 1 over HA. That applies in all circumstances. We also covered the conduction of a wall, plain wall, which equals to L over Ka, which has units of Celsius over watt. For the conduction wall, this can only be true if it meets the same assumptions or circumstances that the cylindrical pipe meets, which is one-dimensional, steady state, no energy being generated, and constant. Okay, that's it for today's class. We went through the heat distribution in a cylindrical pipe. We found that the temperature distribution in a cylindrical pipe is logarithmic, has a logarithmic variation, whereas in the plane wall it has a linear function. We also found the equation for the temperature distribution in a cylindrical pipe or tube. See you in the next video, and that's it.